In this video, we're going to be demonstrating the concept of takt time. We're going to do that by making gingerbread houses. There's a video on YouTube by a company called Game Change Limited, and they have a very funny, humorous video, and educational as well, that where they're assembling gingerbread houses and they're showing some lean concepts. I asked them, do you mind if I add a gingerbread motif to one of my existing models? And they said, no, no problem, go ahead and do that. So that's what I did. So in this model, we've got a customer that demands that we produce 1.25 houses per second normalized. And the front of the house takes 1.5 seconds to make, the back takes 1, the roof takes a half a second, there are 2 sides, each side takes 1 second, and to assemble them all together into the final house takes 1 second. We have 4 cookie making machines that can make any part. Because this is a long run, it's a very long production run, we can ignore the first few seconds while the system warms up. Some other assumptions are that there's no setup time or no changeover time if we switch from one type of cookie to another on a machine. There's no randomness involved, that the times to produce the cookies are known and stable, and that we're going to operate continuously with no breaks. Your instructor can discuss, if some of those are not true, what the impact could be. So let's go ahead to the next screen, and here we can see where we're going to be making the cookies. Our takt time is the 1.25 seconds per part based on customer demand, and we got these 4 machines that are making cookies. They're going to make a cookie, and then they're going to go into one of the 5 bins, so the 5 components that make a house. We have some edible glue, it's sugar based, and that's going to be used to assemble the house, and then they go off the assembly line and we keep a count. So I'm going to go ahead and run this slowly, and I'm going to let you see my control so you know what I'm doing. And you can see it's producing the cookies, and the distances between them are based on the time. The longer the time, the greater the distance. We've already made 3 roofs, but we just finished up the first front. So we're seeing the impact of the time to make each cookie. As they come in, we're getting them in the bins here. Now there's a side, a back, a front. This one's waiting for a side, and then we got plenty of roofs already in stock. So we continue on, and when this side goes into this bin, we'll go ahead and make the gingerbread house. And there it goes. So now we're assembling it, and it goes off the assembly line. We have a count. I'm going to let it run, and what we'll notice is that we're getting way too many roofs and too many backs and fronts as well. The bottleneck is the side. They only take 1 second, but we need 2 of them. So it's a 2-second time that's being achieved because of that. So that's where we're getting this 2 seconds from. And I could go ahead and speed it up a little bit, and you can see that it just gets worse. So it's not a very good solution. We're not meeting the customer demand, and we're getting a lot of inventory stacked up. So we need to come up with a better solution, and we'll let you work on that. What I would suggest is to come up with a better solution. Allow yourself to have a machine that can make different kinds of cookies. You might want to make a side and then a roof, for example. You might want to do a front and then a back, or whatever combination you think is right. Go ahead and write it down, what each machine is producing on this template, and use it as a worksheet. It doesn't need to be neat. You could just do it by hand. And for example, if machine 1 produces a side and that takes 1 second, you'll draw a box around the first 2 blocks and put side, right side on there, just to keep track of what you're doing. And then play with it a bit and see what solution you can come up with to reduce the time. So I'll let you pause the video, and when you restart the video, I'll show you the solution that we came up with. Okay, at this point I'm assuming that you're ready to see the solution, and here's the one we came up with. This is an optimal solution, but it's not the only solution. So you might have a different one that gives the same result. And what we said is if machine 1 does a front then a back, machine 2 does a side, a roof, and a side, machine 3 does a back and a front, and machine 4 does a side, side, and roof. So after 1.5 seconds, we have all the components we need to start assembling the first house, and a second after that, we'll see we have all the components needed for a second house. And then we could just keep repeating this cycle. So when we look at the time between assemblies, we're going to see that the first one says 1 second, because that's going to be the time from when we finish the first to when we finish the second. And then it's going to, the next time will be 1.5 seconds. But over time, it's going to average to 1.25. Let's go ahead and see if that is what really happens in the model. Okay, so I'm going to go ahead and start the model, and here are the controls so you can see them. And here come the components, and they're spaced differently this time, and you notice we're producing them in the order that the solution said, and they're going in. And notice what happened there. Almost immediately it was able to go ahead and produce, because we after 1.5 seconds we had everything we needed. Let's start it up again. So notice we're not getting the cues, and we're better balanced. I'm going to go ahead and speed this up, and you'll see that we do achieve the time of 1.25 seconds per part. Now keep in mind we don't have randomness and some other factors, and we can explore that sometime in the future.